welcome back to another exciting paper solving video. In this video, we are basically going to solve May 2024 Unit 2. This is your favorite Mukdo teacher from Exam Essentials, Mukdo Bhai. So without further ado, let's start. Section A. An enthalpy level diagram for a reaction with an intermediate is shown. Well, you can clearly see that this is down here, the diagram, with the progress of the reaction and the enthalpy provided at the y-axis. They told us which arrow shows the enthalpy change for this reaction. Now, if I talk about arrow B right here, this basically represents the difference, you can say this basically represents the activation energy for the reaction. This represents the activation energy. So that's obviously not the correct answer. We don't actually want that. In this case, C represents the difference in energy between reactants and intermediates. We can clearly see that, while D represents the difference in energy between products and the intermediate. So we can clearly say, and this is the only option available, is arrow A down here, which actually makes sense. This is the arrow that represents the enthalpy change for this reaction. Moving on, you have number 2 down here. The sodium chloride dissolves in water to form a solution because of the interactions between the sodium chloride and water. Now, what are these interactions? Now, if I talk about what happens is that when sodium chloride dissolves, you can clearly know that the sodium ion gets engulfed by the oxygen atoms of water like this. And if I talk about the chloride ions, you can clearly see that the hydrogen atoms basically engulf it like this from the water molecules. Now, obviously, we can say that no hydrogen bond is produced, and on the other hand, there are no significant London forces available when dissolving happens. This is option A and option C. Now, there you can clearly see that there is a interaction happening between a dipole and an ion right here. So the only option here is correct option is C. We tend to see an ion dipole interaction whenever sodium chloride tries to dissolve in water. Moving on, you have number 3, which equation represents the reaction for which the enthalpy change is the mean bond enthalpy of the CCl bond in CCl4. If you check out option A, this basically kind of represents the total energy. If I write it down, total energy required to break all 4 CCl bonds. All 4 Cl bonds in 1 mole of CCl4. This is kind of not correct, you can say. If I talk about the next one down here, now this kind of makes sense because this is the equation representing the breaking of one CCl bond, as it takes 1/4 of a molecule of CCl. So the enthalpy change does here corresponds to the mean bond enthalpy. It represents the mean bond enthalpy of a single CCl bond. Now this is obviously not, the other C and D options are not correct, because we can clearly see that this basically represents the formation of CCl4, not breaking. So we can say that C and D is not correct. So among A and B, A basically represents total energy, so that also becomes irrelevant. So the only option here available is B down here. Moving on, they said which this question is about boiling temperatures right here. So which one is the correct answer? Now, if I talk about the highest boiling temperature, you can clearly say these three are not correct because there are branched compounds which makes their boiling temperatures automatically lower. This is, in other words, is a straight chain. So straight chain ones tend to have the greater number of so more contact area between molecules, and more contact area between molecules results to greater van der Waals force. So our greatest compound with the greatest boiling temperature is option A right here. Moving on, you have which compound is the highest boiling temperature. Again, in this case, we can clearly say that pentane down here, we need to talk about intermolecular bond forces. So here, only London forces are involved. So that's not correct. Obviously, it's the London forces of van der Waals force are the lowest form of intermolecular force of attraction since they're weak in strength. Cyclopentane is also held by London forces as well. This leaves us butanol and butanol diol. Both of them contain hydrogen bonds, but you can clearly see since option D is a diol, there are two hydrogen bonds per molecule. So if there are two hydrogen bonds per molecule, we can easily say that option D is the correct answer because it's going to have the highest boiling temperature among all of the compounds. It's going to, since more heat energy is going to be required to break down two hydrogen bonds relative compared to one hydrogen bond in butanol. Steam is passed over heated magnesium. They said which reaction occurs most readily. Now, if I talk about option A down here, this seems to be the correct answer, but let's analyze the other options. If I talk about B down here, uh, magnesium hydroxide is not produced when you basically uh, heat magnesium with steam, so that is irrelevant. If I talk about C, the formula of magnesium oxide is incorrect. If I talk about D down here, this this does not exist when we basically decompose it. This doesn't exist. So the only option which actually happens is A down here. They told us what are the products formed when lithium nitrate and lithium calcium nitrate are heated separately. Now, when you react lithium nitrate, for example, something like this for LiNO3, it provides us 2Li2O plus 4NO2 plus oxygen. So the products are lithium oxide, nitrogen dioxide, and oxygen for the first case. So this immediately omits A and B from the option, leaving us C and D as the probable answers. Now, if I can find for the calcium nitrate basically provides the reaction as 2CaNO3 which will give us 2CaO plus 4NO2 plus oxygen. So we can see calcium oxide, nitrogen dioxide, and oxygen. So obviously our only correct option is option D down here. Moving on, you can see group 2 compounds provide different colors in the flame test. The best explanation is that the cations have different Yes, the only answer here is the gaps between the electronic energy levels, because that's the only option. Because since there are gaps between electronic energy levels, electrons tend to get excited from their ground state to the higher energy state, and when they return back to their ground state, they tend to emit energy in the form of light, which in the electromagnetic spectrum, making us see a color during the flame test for that specific cation. So A is the correct and most rational answer. If I talk about number 8 down here, the total 2 tests were performed on an unknown ionic compound. You can clearly see there's 2 pieces of information down here. You have silver nitrate, where it was added to an aqueous solution compound, forming a white precipitate. And then a flame test was carried out to provide a red flame. Now, we can clearly see in option A we have calcium iodide, but the problem, this is not correct, because iodide provides a yellow precipitate, which contradicts our result here, which is a white precipitate. Nextly, we can see number B. This would be not correct as well, because bromide here, or bromide ions, is going to provide us a cream precipitate when silver nitrate solution is added, because yellow precipitate is going to provide us AgI, while the cream precipitate is going to be AgBr. So this leaves us C and D. Now, of course, C is not the correct answer, because potassium down here provides us a lilac flame, which contradicts our second statement down here, where a red flame is shown. So the only correct option is D. Moving on, you have number 9. Which compound needs exactly 9 moles of oxygen for complete combustion of 1 mole of the compound down here? For this, we can easily just write the reactions, okay? Okay, so first of all, if we analyze it for the first one, pentane, C5H12, it's something like C5H12 plus 8O2. Then you have 5CO2 plus 6H2O. So if you balance it out, you can see there are 8 moles of oxygen, so that's not the correct answer, because we'll be requiring 9 moles at least. If I talk about B, you have C6H12O, then that means you have 8.5O2, giving us 6 CO2 plus 6 H2O. Again, balancing it, you have 8.5 moles, so that's not correct. We will require 9 moles to be exact. If I talk about this one down here, you have C6H14 plus, it's going to be about 9.502, giving us 6O2 plus 7H2. Again, we have 9.5, not 9, so that's not even correct as well. So the last part, the only option is D, so D is actually the correct answer. Moving on, which solution remains clear on addition to barium chloride solution? Now this is a very nice question. If I talk about here, you can see that when you add dilute sulfuric acid with barium chloride solution, a white precipitate is produced because of the formation of a product called barium sulfate. So that's not correct. B, when you add silver nitrate solution to barium chloride solution, again, what's going to happen is that you're going to get a white precipitate because of the formation of a product called AGCl. Last, we have sodium nitrate and sodium sulfate. Again, sodium sulfate is not correct, because again, a white precipitate called barium sulfate is going to get produced due to the presence of sulfate ions in the solution. So the only option here is C, where when you add sodium nitrate solution, no precipitate is produced, so the solution remains clear. Again, in a titration in 11, a conical flask containing 10 cm cube of 1 mole dm cube of sulfuric acid is fully added. So what they said here is that it's neutralized by 25 cm cube of 0.80 mole per dm cube of potassium hydroxide. The titration was carried out using methyl orange as an indicator. What would be the color change at the end point of the titration? Now, since the solution was sulfuric acid and in methyl orange, the acidic solutions tend to provide red. So it's supposed to be red. So from red, it will go to any other color. So the only option here we can see that it's that provides red to something is option B, so the only option is B. Because at first it was red due to the acidic solution, and then at the end point, when it was near to being neutralized, it turned orange. Moving on, that said, what is the concentration in mole per dm cube of the potassium sulfate solution produced by this reaction at the end point to two significant figures? For that, we need to check out or the balance. We need to find the balanced equation. So if we can write the balanced equation, it's something like H2SO4 plus 2 KOH, giving us K2SO4 plus 2H2O. We can see there's this crazy nice ratio of H2SO4 and KOH is 1 to 2. So we can write the moles of KOH added using the mole ratio right here as 2 times the moles. You can find the moles down here. It's pretty simple. You can find the moles of H2SO4 as the concentration in the volume is provided, which is about 0.0100 mole, right? So you can just write 2 times 0.0100 mole, and basically you get about 2 0.200 mole. So now you know the moles of KOH added. Now you can find the moles of K2SO4 since again the ratio here is 1:1. So you can easily just say, since the ratio of H2SO4 and K2SO4 is 1:1, so you can say that the moles of K2SO4 are 0.100 mole, because 0.0200 mole. It is 0.10100 mole, because one thing that is correct, that is of course the H2SO4 acid down here, you can see it's about 0.0100 mole. So you can say that moles of K2SO4 produced is 0.0100 mole as well. Again, the last part that is left, of course, we need to now find the total volume. Now we know the total volume is about 10 plus 25. So 10 plus 25 provides us 35 cm cube of the total volume down here. So we know the total volume, and now we know the mole, so you can easily find the concentration. The concentration of solution is, you can just divide this mole down here, 0.0100, by 0.03500 down here. If you convert this in dm cube, you get 0.03500 dm cube. So eventually you get about 0.29 mole per dm cube, which is exactly the correct answer. So our only option down here is C, in two significant figures, since they say so A and B is cut, so the only answer is among C and D's answer is C, as we are shown in the calculation. Information about the uncertainties in each reading is used to measure the volumes of the solution in titrates, and as shown, which statement is true? Now, we know in Burette, the initial reading and the final reading is taken, so we need to use this formula down here, that uncertainty is equal to percentage uncertainty is equal to uncertainty times absolute value times 100. So if I find the sulfuric acid, potassium hydroxide uncertainty percentage, we have is 0.05 times 2 divided by the amount of potassium hydroxide required, was the volume was 25.00 cm cube neutralized, so 25.00, which basically resonates to 0.4% down here, right? Again, if I talk about the sulfuric acid, since for pipette we have basically taken just one time, we have used the pipette one time for transferring the sulfuric acid to a conical flask, so we can just find it out as percentage uncertainty is equal to 0.04 divided by, you can say in this case the volume was 10 cm cube for H2SO4, And if you do the math, you get about 0.4% as well. Now we can see that the percentage uncertainty for both the solution is same. So A is actually false. Again, for B, the percentage under the volume substitute is actually 0.4, but it's here they say 0.8%, so that's false as well. This leaves us C and D. Now, if I talk about D, the percentage uncertainty of the volume potential is 0.2. Now, that's not correct because we can clearly see it's about 0.4%. The total percentage uncertainty is, however, 0.8%. It kind of makes sense. So when you add 0.4 and 0.4, you get 0.8% as the total percentage uncertainty of the whole titration. So the only option here is C. Next up, we have number 12 down here. The boiling temperature of the halogens increased down group 7 because on descending the group, the bond polarities increase. Now that is not correct because we know that halogens are diatomic molecules, which means they are non-polar substances. So you can say that that is not correct. If I talk about B, covalent bond strengths increase. Now that is also not correct because we know that covalent bond strengths tend to decrease with increase in the with increase in the bond length. So that is not correct as well. This leaves us C and D. C is obviously not correct because electronegativity decreases down the group. So the only option here is D, because yes, the number of electrons in the molecule increase, which results in an increase in the van der Waals force, and hence more heat energy is required to break the intermolecular forces of attraction between the molecules. So yes, number D is the correct answer. Again, number 13, you have bromine and chlorine each having 2 stable isotopes. Which statement is true? Now, isotopes, whatever they are, the atomic radius kind of remains the same, so that is not correct. The electronegativity also remains the same because actually they're the same elements. Isotopes are from the same elements, so electronegativity does not change. If I talk about C, the first ionization energy of 37 is greater than that of bromine. We know that chlorine and bromine is below chlorine, and we know what happens is the ionization energy decreases down the group, which eventually makes chlorine having higher ionization energy. So this statement is kind of true. So C is actually the correct answer. If I talk about number 14, you have cyclohexane. The density here is 0.78 grams cm cube, and the aqueous iodine, the density is greater than 1 gram per cm cube, and are shaken and left to stand. What colors are the two layers that form? If I talk about the lower layer, now since they say not mention, the solution is whether concentrated or dilute, we can assume that it's dilute. So if it's dilute, and since iodine is a greater density, so we can easily say that the iodine is going to be at the lower layer and cyclohexane is going to settle at the upper layer. Now we know that what's going to happen. What's going to happen is that in the lower layer you're going to find a yellow color of the iodine, and at the upper layer we are going to get a purple color of the cyclohexane because obviously it's going to be at the up. And we know that in D, D is not correct obviously because iodine does not actually show purple color because it tends to stay solid at its within an aqueous solution basically. So B is the correct answer, and A is not correct because obviously, as I said, if it was concentrated, only then A would be correct, and bromine iodine would surely show a brown color solution. But we can see that the upper layer's answer is wrong. It must be purple because cyclohexane's color is purple. So yeah, B is the correct answer. Moving on, we have 4 containers with the same dimensions that hold samples of a gas. The diagram of the Maxwell-Boltzmann distribution of the molecular energy for this gas shows the activation energy, the mean molecular energy, and the most probable molecular energy. For container 2, the temperature is increased. For which values would the energy value change? Now remember one thing, for the change in temperature, the activation energy is not going to change, so that's not correct. The molecular kinetic energy, you can say, in other words, in the most probable molecular energy and the mean molecular energy, so this might change, and the molecular kinetic energy, the mean molecular energy might change as well, because we know that mean molecular energy corresponds to kinetic energy of the molecule, which is about half kT. So kinetic energy here is directly proportional to temperature. So if the temperature increases, then obviously the kinetic energy increases, which in turn results to an increase in the mean molecular energy. So that's going to change as well. So we can say that both changes. So the answer is C. Again, for container 3 at the same temperature, uh, the pressure is lower now, for which value did the number of particles at that value change. Now, since the pressure is lower, so the number of particles is going to decrease for 3 of the values. You can see a lower fraction of molecules are going to possess the activation energy. A lower fraction is going to possess the mean kinetic energy as well. So 3 of them, basically, D. Again, for container 4, the same temperature and pressure as container wall, the walls of the container act as a catalyst for the reaction of the gas, for which values the energy value change. Now, we know that the role of a catalyst is to decrease EA using an alternative route. So the only option that's going to change is the activation energy. So A is the correct answer down here. With this, our section A is completed. Moving on, let us start section B now. Number 16. This question is about the reactions of halogen or alkanes. So when halogen or alkanes are heated with potassium hydroxide, the products depend on the conditions. State what other condition other than a suitable temperature and concentration of potassium hydroxide would give a high yield of but1 and but2 from 2-chlorobutane. Now, obviously, the only condition required for heating halogen alkanes is ethanol with the solvent. Along with the solvent must be dissolved in ethanol. So we can say ethanolic solvent. In this case, the ethanolic solvent, you can say as ethanolic, and you can give the solvent as potassium hydroxide. You can write like that as well. Now give the type of reaction occurring in A1. In A1, obviously, when halogen alkanes react with potassium hydroxide, so hydrogen chloride gets produced as a byproduct. So that's kind of like an elimination reaction. So we can say elimination reaction. State what condition other than a suitable temperature and concentration would give a high yield of butane-1-ol from 1-chlorobutane. We can basically make the potassium hydroxide aqueous. So we can write as aqueous potassium hydroxide, because that would make the that would basically increase the concentration of potassium hydroxide, leading eventually to a greater yield of butane-1-ol than from 1-chlorobutane. Moving on, they said complete the mechanism for the reaction of potassium hydroxide with 1-chlorobutane to form butane-1-ol. So here we go. You have the halogen alkane right here. So if you want to complete the mechanism, what happens is pretty simple. At first, this nucleophile down here, obviously you should do not forget to provide the lone pair of electrons. It attacks the CCl bond right here, and this will basically cause partially positively charged, partially negatively charged to be produced here, which will eventually cause the chlorine atoms to take in the bonded pair of electrons in the CCl bond, and this will cause the Cl minus bond to separate, while the OH gets a chance to react with the reactant join with the empty orbital present in this particular carbon right here produced during the mechanism. Now give 2 reasons why under the conditions used in B2, the reaction between potassium hydroxide and 2-iota-2-methyl propane is faster than the reaction between potassium hydroxide and 1 chlorobutane. First things first, you need to take out that um, 2-iodo 2-methyl propane is a tertiary one, and obviously 1 chlorobutane is a primary halogen alkane. So this basically makes the Ci bond weaker compared to the CCl bond present in the primary halogen alkane. The two reasons basically why the tertiary halogen alkane tends to provide a faster reaction compared to its counterpart. So we can write it down that here 2-iodo 2-methyl propane is a tertiary halogenal alkane, while 1 chlorobutane is a primary one. This makes Ci bond weaker than the CCl bond, for which the tertiary alcohol reacts faster than its counterpart. Moving on, in a titration between a weak acid and a weak base, indicators do not provide a distinct color change. So yes, other techniques must be used. So step one, the procedure was basically the temperature is recorded of 30 cm³ of dilute ethanoic acid, and you can see that later on the ammonia solution was then added to the acid in separate 5 cm³ portions, and then a student carried out the experiment and plotted the graph as you can see very clearly. Find the endpoint volume and the maximum temperature by adding the appropriate lines of best fit to the graph. So first of all, we just need to join these lines, and wherever the intersect, that will be the volume and of the endpoint, and of course the maximum temperature reached as well, that corresponding endpoint. So we can just basically to shape we can just into the shape something like this right here. So if that's the first one, you have, again, if you want to basically again draw a shape something like this, since it's a straight line, so we're basically joining all of them out. And since we are joining all of them out, so we can just ensure that the best one basically gets added. So if we do the math, we can clearly see that the end point is around at, you can see it is around at 21 to be exact. We can see that something like this. See that clearly. You can see that clearly around here. And of course, the maximum temperature we can see it is about 27, so 27.246. It's about somewhere here. So you can say that is, of course, this is about 27.6, and then we have this guy right here, which is 21 cm³. So it's pretty simple. You know the endpoint volume, which is of course 21 cm³, and that's 27.6 degrees Celsius for you. Again, now calculate the number of moles of ammonia added at the endpoint. It's pretty simple, isn't it? You can just divide it with the volume and then get it out. So the amount of moles that you are, so what is it? So if you can basically so what? If we know the volume basically, we know the concentration provided 1.30, so we can just easily do that. 1.30 times, since the endpoint volume is 21, so we just do that math, something like this. So the answer comes to 0.273 mole. Moving on, the next one that said the reaction that occurs is shown. So you have the ethanoic acid reacting with ammonia, and then you have CH3COONH4. Now, this said to calculate the enthalpy change of neutralization for this reaction in kilojoule per mole, giving your answer to an appropriate number of significant figures. This is very important to, as far as that, please underline the part of the question which are requiring you to get the desired answer. For example, the sign must be included, and an appropriate number of significant figures must be maintained when the final answer is provided. So at first, you calculate the mass of water being heated at the endpoint. So mass of water being heated at endpoint down here, which is pretty simple, right? You have 30 plus the endpoint volume is about 21, so that's basically sums up to 51 cm cube. And since the density, they told us to assume the density of all solutions is 1 gram per cm cube, so 51 cm cube represents 51 grams. So that's the actual mass of water. So we can easily calculate the energy transfer using the formula mc del T, where we know the mass is 51.0 with the specific capacity of water as 4.18 times. If you want to find the temperature change, you know the maximum temperature reached was 27.6, while the initial was 20.7, giving us about 1470.9 joules. So that's the amount of energy transfer. Now you can easily divide it in order to find the enthalpy change formula with the mole. So enthalpy change per mole, if you do the math, you have 1470.9 divided by 0.0273, eventually giving the answer as negative 53, since the temperature increased, so the nature of the reaction is exothermic. So yeah, it's 53881 joule per mole. Okay, you can easily just divide it by 1000, giving you the answer to kilojoule, about negative 53.9 kilojoule per mole. Now that is also the correct sign, along with an appropriate significant figure, in this case 3, is provided. Next up, they say number 18 that chlorine dioxide can be used to treat water to make it safe for drinking. The molecule is a free radical. One suggested structure is shown. This is it. Complete the dot and cross diagram for the structure. Use dots for oxygen electrons and crosses for the chlorine atoms. Pretty simple, isn't it? So, according to them, if we just do something like this, we know that there are 6 electrons in the outermost shell of oxygen, and obviously a double bond is going to get produced, as you can see clearly right here. So a pair of electrons must be shared, so something like this. And we know there are 7 electrons to be accommodated in the outer shell, so in chlorine. So yeah, there we go. And while a single bond right here is produced with oxygen, while the rest 6 electrons are present already in oxygen down here. So this is the complete dot and cross diagram for the structure, where 3 of the shells have been fulfilled. Give the reason why chlorine dioxide is not a linear molecule. The reason why is that chlorine has non-bonding electrons in its outer shell, which repels the bonding pairs of electrons. Now, you should know that lone pair bond pair repulsion is the greatest, and after that you have lone pair repulsion, and at last bond pair repulsion. In this case, we can clearly see that oxygen atoms are containing the lone pairs. In fact, two lone pairs in individual oxygen atoms. So what is happening? And we also have the non-bonding electrons and chlorine atom as well. The lone pairs right here. So what happens is that the combination of the repulsion being faced between the oxygen lone pair electrons and the lone pair electrons of chlorine enables them to not become a linear molecule rather than becoming, uh, in other words, what can we say? Trigonal pyramidal shape, just like ammonia basically. Now moving on, we can see that chlorine dioxide can be made from potassium chlorate in a two-step process. You have step 1, potassium chloride 5 reacts with concentrated sulfuric acid to form compound A, and then compound A then undergoes a disproportionation reaction. Right, state the meaning of the Roman numerals in chloride 5 and chloride 6. Well, it's pretty simple, right? In the Roman, you can say that the Roman numerals is what? The charge the chlorine would have if species were fully ionic. Okay, moving on, state the oxidation number of chlorine dioxide. Okay, that's pretty simple. Okay, if you want to find the chlorine dioxide right here, it's pretty simple. It's about +4 if you do the math. So the oxidation number is +4. Now in step 2, compound A undergoes disproportionation. Deduce the possible range of oxidation number for the chlorine compound A, and how do you justify your answer? Now, when it undergoes disproportionation, what happens? Basically, it once basically gets reduced, and again it gets oxidized at the same reaction. Right. So they say deduce the possible range of oxidation for the chlorine. Well, it's pretty simple. It must be either between either it's maybe either +5 or +6. Why is it the case? Because it must be between +4 and +7. Now +4 is obviously not possible because we know that it's the before the react it's basically the initial oxidation number. The only thing that's possible is +5 or +7. There's going to be a 3 electron increase or 2 electron increase from the initial state. Okay, because if it does not happen, then the other reactant, in other words K03, is not going to get oxidized or reduced, sorry. Again, if you move on to the next one, you have compound A has molar mass 84.5 and the composition by mass of this much. This is the molecular formula of compound A, showing all your working. So first of all, let's calculate the percentage mass of oxygen. Since all other are provided, you can just omit 100 minus 1.18 minus 42.01, eventually giving us 56.81 percentage of oxygen. Now we can basically we can draw a table, basically something like this, right? And you can easily do the math down here. So down here you have and then if you do another one and rotate it, Sorry about that. In this table, we are basically going to throw the calculations. So it's going to take a little bit of while down here. Uh, Anyways, so if you do the math like this, so you have HCl and O, and if you just divide it with their molar masses down here, what do you get? Eventually, the thing that you get is 1, and here you get as 1 as well. And then here, when you do the calc, you get 1. So what can we say? What is the mass of HClO3, isn't it? So we can find the mass of HClO3 since the ratio is 1:1:3. So the mass of HClO3 is pretty simple. You have 1 plus 35.5 plus 16 times 3, giving us 84.5 gram per mole as the molar mass. And that basically is the molecular formula of the compound. And that is actually the molar mass which is provided. So our compound as reduction is actually correct. Let's move on to the next one. Write an equation for each of the two steps in the formation of chlorine dioxide using your answers in B. Using our answers in B. So as you can see, since the oxidation number, since we predicted it, so we can easily write down the stuff. The first reaction that occurs is that 2KClO3 reacting with sulfuric acid. The potassium chloride 5 reacting with sulfuric acid provided us 8ClO3 as one of the product and K2SO4. In the second step, what happens is that this guy right here, the product 8ClO3, basically reacts with basically what? Not react. It basically you know goes under disproportionation reaction, causing the chlorine to get oxidized once and then reduced again to 8ClO4 plus water. If you want to balance it, you can just give it 2 right here and 3 right there. These are the two equations for the formation of chlorine dioxide. Eventually, chlorine dioxide is produced as one of the product in the second reaction. One industrial preparation of ethanol is by the catalyzed hydration of ethene via a reversible reaction. So this is the reaction provided. Identify by the name or formula the catalyst used for this. This is the basically the hydrolysis process. So the hydration process using steam, and we basically tend to use phosphoric acid. Okay, you can also write H3PO4 as well. Under these conditions, the conversion of ethene to ethanol is 5% at equilibrium, but the overall yield of ethanol for the process is 95%. Suggest what happens to the equilibrium mixture containing ethanol so that the overall yield of ethanol becomes 95%. Look, first of all, what we do is that the reaction mixture is cooled. Why is it cool? Why it's cooled? So that the ethanol and excess water liquefies. On the other hand, the unused ethene gets recycled at its gaseous state. This is what is going to happen. So the unused ethene is going to get recycled again to produce in the equilibrium mixture in order to basically produce to ethanol again. The temperature used is 300 degrees Celsius and the pressure is about 7 megapascal. And the amount of water present in the reaction mixture are all compromises. Now explain why the temperature used is a compromise. Well, first of all, you need to understand here that the forward reaction as provided using the value right here, that means the forward reaction has an exothermic nature, right? So if it's exothermic, so it's favored by a low temperature because at lower temperature, the reaction or the equilibrium shifts towards the right, giving us a better yield. But the lower temperature also results in a rate of reaction which is too slow to be economically viable. Hence, we can say the temperature used is a compromise. So we can write it down. The forward reaction is exothermic, and so is favored by a lower temperature, giving a higher yield. But the lower temperature would also at the same time result to a slower reaction to be economical viable. Hence, we can say the temperature used is a compromise right here. Explain why a manufacturer might suggest a pressure greater than the compromised pressure of 7 megapascal. Well, if that's the case, because if you increase the pressure, what's going to happen? We can clearly see the product side contains less number of moles. Here we see 2 mole as opposed to 1 at the product side. So obviously the equilibrium is going to shift towards the right. Hence, this is because because of the fewer moles. So obviously a greater yield of ethanol can be produced or can be achieved basically. So we can write it down that the equilibrium shifts towards the right, giving a greater yield of ethanol because there are fewer moles of gas on the product side, or you can say right hand side. Moving on, at pressures greater than 7 megapascals, a waxy solid forms which melts over a range of temperatures. Identify by the name or formula this solid. Well, it's pretty simple. It's going to be the waxy solid in this case. If we analyze right here, it's going to be polyethenes because one of the reactant is ethene, so we can just write it down as polyethene. This basically melts over a range of temperatures because polyethylene does not have a particular boiling melting point. Now give one other reason for not operating the process at a pressure greater than 7 megapascal. They're also told to not include safety considerations in your answers. So first of all, the only one reason we can suggest is that higher pressures require special equipment. Withstand this higher pressure. This makes the whole process expensive. Exactly. So if you basically use a pressure greater than 7 megapascal, you'll be requiring to buy or export equipments that can withstand that pressure. So this will overall increase the cost and make the whole process more expensive. Increasing the amount of water in the reaction mixture without changing the pressure might also be suggested. It's just one advantage and disadvantage of increasing the amount of water. Well, one advantage we can clearly say is that it pushes the equilibrium to the right because we know what one of the reactants is, of course, uh, is water. So obviously it's going to basically shift the equilibrium to the right at the lower concentration side. So we can say is that it pushes the equilibrium to the right, hence increasing the yield of ethanol. The only disadvantage is that there is more water condensed with the ethanol to separate. That's going to eventually, the whole mixture is basically going to be more impure. So we can just rate said disadvantage is that there is more water condensed with the ethanol to separate during purification process. So this eventually basically decreases the purity of the whole mixture. Okay, so that's basically it. And with this, we're done with section B. So now let's move on to the next part of our paper, which is section C. Now let's say that terpenes and terpenoids are groups of chemicals found in plants. They contribute to the smell and taste for the plant, so are used in flavorings and perfumes. Both terpenes and terpenoids have carbon skeletons on one or more units of the compound isoprene. So you've got isoprene down here. Terpenes are made up of two or more isoprene units joined together, while terpenoids have additional functional groups, often containing oxygen. So these are some additional information provided. Give the IUPAC name for isoprene. So exactly, if we see that, we can see that there are two alkene functional group, and all of them, well, this one is present in carbon 2 and this is present in carbon 3. So we can say that we can see that what we can clearly see that with the second carbon, a methyl group is attached down here. So you can write it down as 2-methyl. You can write it down as 2-methyl, um, 2-methyl and that is one carbon down here. So we can just write this carbon and this carbon, 1, 2, 3. So we can give as 2-methyl, and since the straight chain is consists of 4 carbons, obviously it's going to be buta 1,3-diene. The diene basically comes from due to the presence of alkene functional group present in this isoprene compound. The peaks with the highest intensity in the mass spectrum of isoprene are at mass to charge ratio of 68 and then 53 respectively. So what might be it? The first one is pretty simple. You can just write it down as CH2 double bond C. The methyl group is coming down here, which is obviously connected with CH2Cl. Again, for 53, it is CH2 double bond C. The methyl group goes away while the rest of the molecule remains the same. So these are the two peaks, or the species responsible for these two peaks in the mass spectrum of isoprene. There we go. You have the infrared spectrum of isoprene being shown. And for this, you need to check out the spectrum right here. You have transmittance and the wave number. The question says, state the origins of the peak labeled P, Q, and R, and you may use the label diagram and use the data booklet as a source of information. So this is the data booklet right here. If you see for P, it is between the ranges of 3,200 and 100. And if you see that, check out the data booklet right here. For this, we have pretty simple. We have the CH vibrations. So we can say that P is due to CH vibrations, uh, which signifies the presence of alkene. Again, if I talk about Q, again, Q, as we can see, what Q also is within the same range, a little bit backwards, for example, between 2,900 and 3,000. So Q again is due to CH vibrations, which signify the the presence of alkane group. And if I talk about R, it's again where is R? R is within, you can say, between 2,000. It's between 1,002, 4, 7, 8, 10. So it's between 1, 2, 3, 4, 5, 6. Between 1,600 and 700. Again, basically representing an alkene. So you can just write according to data booklet. R is due to the due to what? Due to carbon to due to carbon to carbon group, which signifies the presence of alkene group in the compound. So since our analysis is complete, we can just write the compound. We can just write the compound along with the peak values. So we can just write it down as, at first, let's draw the structure. If we draw the structure, something like this, as per stated in the previous, in the above part of the question. H, and then you have a methyl group attached, and there's an H right here. So this one is going to have P due to this one, and this is for R. That is also for R, and this is going to have for P, and for this we have Q because it is a methyl group down here. For this you're going to have also P, and again, yeah, this is it. For this we're going to have P as well. So like this is how you basically label the whole structure along with after the analysis from the infrared spectrum isoprene as shown. Next question, moving on. Show that mycrene and limonene are terpenes by comparing the molecular or the empirical formulae of micrine, limonene, and isoprene. If that's the case, you can see that the molecular formula of either micrine, limonene is C10H16, because we can see very clearly that there are 10 carbons in 3 of these compounds, and also, in other words, there are also what? There are also 16 hydrogens in 3 of the compounds, if you count so. So if that's the case, we can say one thing: the molecular, it's like basically writing the similarities between these 3 compounds. The molecular formulae of 3 of these of limonene and and micrine is same C6H16, sorry, 10 actually, as isoprene. So we can easily say the molecular. So we can easily say what? So we can say that the molecular formula of micrine and limonene is twice of isoprene. So they are terpenes. Um, so terpenes, because we know that in the previous part of the question they said what? They said that limonene and micrine are both terpenes composed of 2 isoprene units. So if there are 2 isoprene units, which you can see very clearly, because if we, that since the molecular formula of micrine and limonene are twice of isoprene, so 2 isoprene units, hence we can conclude that they are terpenes. So we can say, since the molecular formula of micrine and limonene is twice of isoprene, we can say they are terpenes. Both micrine and limonene can be completely hydrogenated by reaction with hydrogen. State the conditions required for the hydrogenation of alkenes. Now remember, the only condition that you will be requiring, and it's also provided in our S level course, which you have studied previously, is that you'll be requiring heat and nickel catalyst in order to speed up this hydrogenation reaction. These are the main conditions for hydrogenation of alkenes. Lastly, they said that 5-gram samples of micrine and limonene were completely hydrogenated. To calculate the volume of hydrogen required to hydrogenate each sample, and you should include the unit with your answer. The first things first, you calculate the molar mass of terpene and hence its mole. So we know the molar mass of terpene by calculating the molar mass of terpene. If you calculate from the above molecular formula, it is about 136 gram per mole. And so, since now you know 5 gram down here, so we can easily say that moles of terpene is 5 divided by 136, which eventually gives us 0.0366765 mole. So this is the moles of terpene. Now since we know the moles of terpene, we can now find the number of moles of hydrogen required both there. So we can just create a shape, something like this. Okay. And then we can just do like this. So this is going to be micrine, and that is going to be for the limonene. So what happens, you calculate the number of moles of hydrogen required. So since you now know the moles of micron, which is 0.03675, for both it's actually kind of the same. The only thing that you need to check out is that, as this said here clearly, that the mole ratio, if you check out the mole ratio, it is about 3:2. So if you do that, you have, of course, times 3, that is times 2, and now the moles is pretty simple, which literally comes as 0.11030, and the moles for this one comes as 0.753, 0.07353 moles of hydrogen. Now, pretty simple. You can now find easily the volume of hydrogen in each case. Since the volume of 1 mole of hydrogen is provided, which is about 24,000 cm cube, we can just multiply each of the moles with the provided value. So, times 24,000, this one, and 0.078353 to be honest, sorry, times 24,000. Eventually, if you just plug it in the calculator, you'll be able to get 2647.2 cm cube, and for that you have 1764.7 cm cube. So this is the amount, the volume of hydrogen required to hydrogenate each sample. If I say so, these are the final answers you can say for each of the sample. For micrine, it's this much, and for limonene, it's this much. Moving on, give the IUPAC name of the product formed by the complete hydrogenation of micrine. So when you basically do the complete hydrogenation of micrine, is that what happens is that in the 2, 3, 4, 5, 6, in the sixth carbon, and in the second carbon, we can see there's a methyl group. In the sixth carbon, what happens is that one of the double bond basically gets broken down. So either you basically so hydrogen bond and hydrogen is attached, and 1, 2, 3, 4, 5, 6, 7, 8. Since there are 8 carbon in the main straight chain of the compound, so we can say it's an octane. So the IUPAC name is, of course, 2,6-dimethyl, since there are 2 methyl groups connected in 2 and 6 carbon atom, respectively. And the main chain is an octane, so we can write octane. So the whole name is 2,6-dimethyl octane after complete hydrogenation of micrine occurs. Moving on, the last question, they said, uh, 3 students were asked to carry out a single chemical test to unambiguously identify the presence of OH group in the 3 terpenoid compounds: menthol, linalool, citronellol. These are the 3 compounds as provided. You can see that. So the next thing, the first student tried using acidified potassium dichromate 6 to oxidize the alcohols. The second tried acidified potassium manganate 6, an oxidizing agent similar to potassium dichromate 6, while the third student tried using phosphorus 5 chloride. Criticize the 3 students' suggestions by linking the expected results and the actual observations that would be made. Remember, criticizing basically means taking out the positive sides as well as taking the negative sides as well. Okay, first of all, what happens when potassium dichromate 6 is added? So when K2Cr2O7 is added to 3 of them, uh, is added to 3 of the alcohols, the change that we would see is that it would go orange to green with menthol and linalool, but it would stay the same for citro. I mean, it's going to go from orange to green from menthol and citronellol, but it's not going to change for linalool. Uh, this is because the only reason here is that menthol and citronellol, you can see that these are not tertiary alcohol, Unlike this one right here, these are, you can check it out, that you can check that these are, one is a secondary alcohol while the other one is a primary alcohol. But linalool is a tertiary alcohol. So this is not, it's not going to get oxidized by the oxidizing agent. So we can write that for menthol and citronellol, the solution goes from orange to green, but would stay the same for the other compound alcohol, which is linalool. For linalool, this is because menthol and citronellol gets oxidized while as it is tertiary alcohol. Okay, so this is the first part of the stuff. Secondly, the second tried potassium manganate 6, an oxidizing agent similar to potassium dichromate 6. So if we criticize the second student, what's going to happen that potassium manganate 6 is not a good choice, first of all? Well, this is because when you add it with all three alcohols, it would go from purple to colorless. As a result, it won't be able to accurately identify the presence of the OH group, as it is also going to react with carbon to carbon double bond again in order to produce a diol with linalool and citronellol. Like, as for example, since there are carbon to carbon double bond in linalool and citronellol, so it's going to further oxidize alkene, producing diols. As a result, the whole point of adding potassium manganate 6, that is to identify which group, that won't be achieved, because we won't be able to distinguish for what, for exactly for which thing the color change took place. So we can write it down that potassium manganate 7 is not a good choice because with all three alcohols, the solution goes from purple to colorless, but the identification of OH group will not be will not happen, as the oxidizing agent further reacts with carbon to carbon double bond group present in linalool and citronellol to produce diols as further products. So as a result, we won't be able to identify, or the OH group accurately, the presence of OH group accurately. The third student tried using phosphorus 5 chloride. Now, phosphorus 5 chloride is obviously a great change, because phosphorus 5 chloride is going to produce misty fumes in for three of the alcohols due to the presence of OH group, and this greatly identifies the presence of OH group, because it's going to react with all type of alcohol. Because, and since there are three types of alcohol present, you have the primary, you have secondary, also you have a tertiary one. So we'll be requiring something that should react with three of the alcohols, with three types of alcohols. The phosphorus 5 chloride is actually the best choice here, because it's going to react. So we can write it down that phosphorus, while we criticize the third student's experiment, the phosphorus chloride is the best choice, as it will produce misty fumes with all three alcohols, and help us and help to identify the presence of OH group in them, as it has the capability to react with all primary, secondary, and tertiary type alcohols. So this is how you basically write the 6-mark question, while you criticize the observations of the 3 students who have performed this experiment. Along with this, our section C is complete. Hoping you guys to join with another exciting paper solving video at the future. So along with that, bye bye.